the most common ways in which energy transfers from one place to another, or even from one object to another, is in the form of waves. Mechanical waves are a type of wave that transfers through a medium. A medium is simply some type of matter that a wave can travel through. The medium for a sound waves I am producing is air. The medium for the wave a surfer catches is water. The medium for the trembling waves caused by an earthquake is the solid surface of the earth. We will discuss three types of mechanical waves. The first type we will observe is called a transverse wave. If you close your eyes and picture a wave in your mind, you would most likely picture a transverse wave. The medium for our transverse waves is this metal slinky. The blue line represents the rest position of the slinky. Notice there are two pieces of blue tape on the slinky. This is to help you better visualize one coil on the slinky. Observe that the wave travels right and left across the screen as wave pulses are sent down the slinky. However, if you look at the pieces of tape, they are moving up and down as the energy from the wave passes through them. The motion of the medium and the motion of the wave are perpendicular to each other. Now let's look at a continuous series of transverse waves in order to identify other wave characteristics. Once again, notice how the wave is traveling right and left on the screen, but the individual coils on the slinky, indicated by the pieces of tape, are moving perpendicular to that motion. The pieces of tape are moving up and down. The highest point a transverse wave reaches in relation to the rest position is called a crest, while the lowest point the wave reaches is known as a trough. If you were to measure the distance from the beginning of a crest to the end of a trough, you would have the wavelength of a transverse wave. Notice that as you move from the beginning of a crest to the end of a trough, the wave begins to repeat itself. At the end of the trough, the wave is starting to crest again. The wavelength is a measurement between two identical points on a wave. You could just as easily measure the wavelength from the crest of one wave to the crest of the next wave, or even from trough to trough. It is relevant to notice that for a transverse wave, one wavelength always includes one crest and one trough. One final wave characteristic that needs to be addressed is the amplitude of a wave. Amplitude is simply the size of the wave. More specifically, amplitude is the maximum displacement of the particles of a wave measured from the rest position. For mechanical waves, the energy of the wave depends on the amplitude of the wave. The larger the amplitude, the more energy a wave has. The waves at the top of the screen have a larger amplitude than the waves at the bottom of the screen. Therefore, the waves at the top of the screen are transferring more energy. A common mistake made by students is to measure the amplitude from the crest to the trough. Note that this is incorrect. Amplitude is always measured from a crest to the rest position or from a trough to the rest position. The second type of mechanical wave we will observe is a longitudinal wave. The slinky will still be used as the medium for the longitudinal waves, and once again, the blue line represents the resting position of the slinky. Just as with the transverse waves, the longitudinal wave travels right and left across the screen as wave pulses are sent down the slinky. This time, however, the pieces of tape are moving right and left as the energy from the wave passes through them. The motion of the medium and the motion of the wave are parallel to each other. Instead of crests and troughs, longitudinal waves have compressions and rarefactions. Compressions are the bunched up areas of the wave, while rarefactions are the expanded areas of the wave. The wavelength of a longitudinal wave can be found by measuring the distance from the beginning of a compression to the end of a rarefaction. Since wavelength is a measurement between two identical points on a wave, you could just as easily measure the wavelength from the compression of one wave to the compression of the next wave, or even from a rarefaction to a rarefaction. For a longitudinal wave, one wavelength includes one compression and one rarefaction. Longitudinal waves do have an amplitude, but it's easier to observe the amplitude of a longitudinal wave with your sense of hearing. Sound waves are excellent examples of longitudinal waves. To increase the amplitude or energy of a sound wave, simply increase the volume. The third and final type of mechanical wave is surface waves. Surface waves travel on the boundary between two media. Rayleigh waves are surface waves produced by an earthquake. They travel on the boundary between the earth and the air. Water waves are surface waves. They travel on the boundary between water and air. Surface waves have the properties of both transverse and longitudinal waves. The particles of the medium will travel both perpendicular and parallel to the direction of the wave. This results in the particles of the medium traveling in a circular pattern, much like the leaf shown in this animation. If you follow the motion of the leaf, it moves in a circle while remaining in a relatively fixed position. Let's use these surface waves to examine a couple more characteristics of waves involving the speed of waves. The first of these characteristics is the period of the wave, which is simply the time it takes for a wave to repeat itself, the time per wave. Let's count how many waves pass by this mark during a 10-second interval. In this case, we will measure the wavelength from crest to crest. During a 10-second interval, 6.5 waves pass the mark. Therefore, the period can be found by taking the time, 10 seconds, and dividing by the number of repetitions, 6.5 waves. The period of these waves is about 1.54 seconds per wave. The frequency of a wave is simply how frequently waves pass a point over time. In the case we just examined, 6.5 waves pass by during 10 seconds. The frequency of the waves is 0.65 waves per second, or hertz. Notice that period and frequency are simply inverses of each other. The period was 10 seconds for 6.5 waves, while the frequency was 6.5 waves in 10 seconds. Now, if we have either the period or the frequency, and we know the wavelength of the waves, then we can determine the speed of the waves. The wavelength of the surface waves in this animation is 2 meters. To find the wave speed using the period, simply take the wavelength and divide by the period. The symbol for wavelength is the Greek letter lambda, which looks like an upside down Y or a teepee. The symbol for period is a capital T. In this case, 2 meters divided by 1.54 seconds equals 1.3 meters per second. We can get the same answer by multiplying the wavelength times the frequency. The symbol for frequency is a lowercase f. So 2 meters times 0.65 hertz, or waves per second, equals 1.3 meters per second. Both methods arrive at the same answer, and that is simply because period and frequency are inverses of each other. This concludes our discussion of mechanical waves and their properties. So until next time.